we're making sure that the notes last night made sense. If your notes last night were already on graph paper, you can just add this to last night's notes. The graph paper that I made you grab is only for people who took their notes last night on notebook paper. Then this is going to be good to have some graph paper examples, okay? All right, so we just want to make sure that we are comfortable doing other representations of inverses. So yesterday we stuck specifically with equations. Today we're going to focus a little bit more on working with tables and points and things like that. There will be some equations for today's assignment, but we're going to be focusing more on the other representations instead, okay? So what I want to do first is actually start off with an equation. The equation we're going to start with is y equals the square root of x minus 2. And what we're going to do is we're just going to take what we know about square root graphs and we're going to find some information about it. And then we're going to use that information and we're going to go through and we're going to find the inverse. Okay, so this is just a continuation of our notes from last night. If you're putting a title on these notes, you're just going to say inverses of tables and graphs. Okay, inverses of tables and graphs. Okay, all right, so what points do we usually use for square roots? If you don't remember, it's on the board still. 0, 0, 1, 1, and 4, 2. And if I wanted one more point, what's another point I could do? 9, 3, perfect. So the square root of 9 is 3, which is why that's another point I could use. The square root of 9 is 3. Okay, so what is the transformation that's happening to this graph right here? Right 2, and so what are all these points going to do? Am I changing the x coordinate or the y coordinate? The x. So I'm going to go plus 2, plus 2, plus 2, plus 2. So I probably didn't need that last point, actually. I'm probably not going to even graph it, to be honest. And then all my y coordinates are actually going to stay the same. Okay. Now, our x's are going to get pretty big. We're going from 2 to 11. Our y's not so much. But even though our y's don't get big, since we're doing inverses, I'm going to have you draw your graph big enough so that your x's can get to about 12 and so that your y's can get to about 12, okay? So we want a graph where the first quadrant, your positive x's and your positive y's, can both go to 12. So just count, make sure you got enough boxes. I'm just putting the 5 and 10 in there so it'll be easier for me to count as I plot my points. All right, how do you guys feel so far? We okay? Here, let me make it easier to see. Okay, so let's go ahead and plot the points. So we've got 2, 0, and 3, 1, and 6, 2, and then 11, 3. So there is our graph. And then let's just find some information about this graph. So can somebody tell me what the domain of this graph is? It's 2 to infinity. So the furthest left that the graph goes is 2. On the x-axis, if we think about the x values, we can see the furthest left that it goes is 2. The furthest right that it goes is an arrow. It goes right forever. So the furthest left that it goes is 2. The furthest right that it goes is an arrow. I know infinities always get parentheses, but what about the 2? Should the 2 get a parenthesis or should it get a bracket? Bracket, that's a point. I can put my finger on it. That's a bracket. All right, what about the range? 0 to infinity. So the furthest down that it goes is a y-coordinate of 0. The furthest up that it goes is a y-coordinate of positive infinity, right? It's going up forever. So 0 to infinity. Infinity gets a parenthesis. What does 0 get? A bracket. Okay. What is the x-intercept? 2, 0. Okay, what is the y-intercept? None. Okay. I need you to switch colors. So grab a marker, grab a colored pencil, grab a pen, grab something different colored. I have tons of colored pencils, markers up here, so grab whatever you need to switch colors. All right. So yesterday we did all of our inverses by trading the x and y in the equation and solving for y. Today we're going to do most of our inverses by trading x and y coordinates. So I'm not going to work with this equation to find my inverse. I'm going to work with the points. So I'm going to take the 0, 2 and I'm going to switch it. Or sorry, I'm going to take the 2, 0 and switch it to 0, 2. I'm going to take the 3, 1 and switch it to 1, 3. I'm going to take the 6, 2 and switch it to 2, 6. I'm going to take the 11, 3 and switch it to 3, 11. And then I'm going to plot those points. Okay? So I've got 0, 2, 1, 3, 2, 6, and 3, 11. And then I want to find the same information for my inverse graph. So what is the domain for my inverse graph? What are the x values that you can see? 0 to infinity. Okay. What is the range for my inverse graph? 2 to infinity. What is the x-intercept for my inverse graph? None, it doesn't touch the x-axis. And what is the y-intercept? 0, 2. Okay. Everything switches. So let's clarify that a little bit. So domain represents the x values. And so when we found the inverse, that switched and it became something that represented the y values. The range of the original function represents the y values. So when we found the inverse, that became something that represented the x values. Does that make sense? Now, individual points, they have something that has an x and a y coordinate, right? So we had the x-intercept, but the x-intercept had an x and a y coordinate. So we switched those from 2, 0 to 0, 2. So the x-intercept became a y coordinate, but those two numbers also switched places. Do you see how in these the numbers did not switch places? See how they don't switch places? That's because this is an x and an x. They're not switching places because they're both x values. These are not switching places because they're both y values, so they shouldn't switch places. They just switched what they represented. Okay? So over here it was x, x, so over here it became y, y. So things still did what inverses do. They went from x's to y's. So they don't have to switch places always, but things that represent x's and things that represent y's, those always switch. Does that make sense? Okay, so things that represented x's, things that represented y's, those traded. Things that represented y's and things that represented x's, those traded. And then these things, we had one of each here. So we had an x and a y. Those actually traded places. 0, 2, or 2, 0 became 0, 2. It was an x-intercept. It became a y-intercept. We used to not have a y-intercept. Now we don't have an x-intercept. Does that make sense? Okay, now let's do a little bit of the work that we did yesterday. So now I'm going to go ahead and take this equation. I'm still using my other color. And I'm going to trade the x and the y value. I have x equals square root of y minus 2. So based on what I learned yesterday, what should I be doing? How do I get the y alone? Square both sides. Okay, so I'm going to square the x, and I'm going to square the square root. So squaring the square root, those two operations cancel each other out. They're inverses of each other. And then I get x squared equals y minus 2. And then what do I do? Add the 2 over. I get x squared plus 2 equals y. And so I'm done. The y is alone, but I want to make sure this looks correct. Put the inverse notation, y inverse equals x squared plus 2. So there's my inverse equation right there. Now this looks like a parabola that has no left and right shift, that has only been shifted up 2. But if you look at the picture, does the picture look like a parabola? No, kind of, right? Yeah, it only looks like half of a parabola. So, yeah, if we drew more of it, it would eventually turn into one. So the trick is, though, we know that the way that inverses work is you're supposed to take the points and you're supposed to trade the x's and the y's and you're supposed to draw them, right? So we found the inverse correctly. We found it correctly. We didn't do anything wrong. But when we found it, we only found half of a parabola. So this here is one of the tricky parts of math, because technically the inverse of a square root function is actually only half of a parabola. Technically, it's only half. So we actually say it's a parabola, and we say it's a parabola with the domain of 0 to infinity, and we're actually supposed to state that. All right? Am I going to test you on this? No. Okay, this is just interesting information. When you get into higher math, they start to ask you questions like this. At this level math, they find it interesting. They would like students to be aware of this, that you should know that if you're taking the inverse of a square root function, that a square root function is only really half of a parabola. It's not a whole parabola, which I think if we look at it, we can tell, yeah, only half of it's there. The other half is missing, okay? Now, I'm going to show you guys kind of the opposite effect, because since these are inverses of each other, in theory, if we were to take this, we should get back to the square root, right? I'm going to answer your question in a minute. Okay, I can see your hand. So let's start here. Let's take the y equals x squared plus 2, and I'm going to show you guys how it gets back to the square root, and I'm going to show you where the interesting part is happening, okay? So if we traded the x and y, x equals y squared plus 2, what would we do first? Minus 2. X minus 2 equals y squared. And then what would you do? Square root. And what have teachers in the past told you that you have to be careful of when you square root something? What are you supposed to put in front of a square root when you're the one doing the square root? How many answers do you get when you square root something? 2. What are you supposed to put in front of a square root? A plus or minus, okay? So you're supposed to, anytime you are the one doing the square root, you're supposed to put a plus or minus in front. Now, typically when we teach inverse functions like what I taught you guys yesterday for the very first time, I did not tell you to put a plus or minus in the front because that's confusing for students the very first time they learn it, okay? Am I going to ask you to start putting a plus or minus in front every time you do it? No. If we were solving an equation, I would make you, but no, I'm not going to make you do this every time we find inverses, but I'm going to show you if we have y equals plus or minus the square root of x minus 2, if I graph this, this is actually two different graphs. It's the square root of x minus 2, and it's the negative version of the square root of x minus 2. What do you guys think the negative version of the square root of x minus 2 looks like? It's the other half of the parabola. Does that make sense? Okay. So it's something that you are just going to be a little bit aware of. Is it something I'm going to test you on explicitly? No. But in an honors math 3 class, if I never told you about it, I would not be a very good teacher. Okay. So that is why I showed you guys on the graphing day, because on the graphing day, it's a little bit easier to see because you're looking at points. It's easier to see it from points than it is to see it from the equation. Okay. So for today, you're going to see things like this where we're dealing with like, oh, that's only half a parabola. That's not the whole parabola. Okay. Any questions on what I just showed you? Does that make sense? Do we see how the domain can go to the range of the inverse? Can we see how the range can go to the domain? Okay. Now I want to show you guys some notation stuff. Okay. We're going to talk about some notation. Okay, so if they were saying something about the original function, they would say maybe for that beginning problem, they might say f of 3 equals 1. So that was one of the points we had. If you plugged in an x coordinate of 3, you got a y coordinate of 1. They might say an x coordinate of 6 equals a y coordinate of 2. You guys see those are 2 points that we graphed? Then for the inverse, they would say f inverse of 1 equals 3. See how that just switches the 2 points, traded x and y? Traded the 1 and the 3. And then they'd say f inverse of 2 equals 6. Does that make sense? Okay. So that is some notation that you might see today. They'll say, hey, if the function has f of 4 equals 11, what can you tell me about the inverse? What would you tell me about the inverse? F inverse of 11 equals 4. Okay. What if I told you that the domain of f of x was 3 to infinity, and I wanted you to tell me something about f inverse of x? What could you tell me? If I said the domain of f of x was 3 to infinity, and then I wanted you to tell me about something about f inverse of x, then you would say, well, if that's true of f of x, then that means that the range of f inverse of x is 3 infinity. Does that make sense? So this was a description of the x's for the original function. That means it must be a description of the y's of the inverse function. Does that make sense? So the main idea about inverses is that x's and y's trade. That's the main idea, okay? X's and Y's trade. Now notice these two things did not trade spots because this was an X and an X and it became a Y and a Y. So they didn't have to trade spots. We're not always trading spots. We're trading what represents an X, what represents a Y. Okay? All right, how do your brains feel about that? Brains are comfortable? Okay, so I'm going to give you guys a worksheet. It has a mixture. Some of the representations are graphs, and you just have to grab some points off the graph so that you can trade the X's and Y's and then redraw it. Some of the things on there are points. Some of the things have to do with domain and range. There's all sorts of different representations on there. Your goal of the day is just to understand how can I trade these things. Does that make sense? Yes? Okay.